this computer. Okay, very good. We might have another couple of people come along, but welcome everybody for now. We are extremely happy to have Félix Chalumeau here to talk to us today. Félix graduated from École Polytechnique and the Imperial College in Applied Maths and Machine Learning. He's been working at Institute for a while now and is really a world expert, leading expert on the topic that he's going to be talking to us today. So we're very lucky to have him here. And he's going to be talking about reinforcement learning for combinatorial optimization, and I hope about the compass method. Yeah, over to you. Thank you.
Great. Thank you very much for the introduction. It's a pleasure for me also to be there and talk to you a bit about what I've been doing over the past years. So yeah, thanks for attending. So I guess again, are we waiting a few more minutes for some other joiners, or should I just?
There might be a couple more people come along, but I think we can start for now. This is good.
All right.
Yeah.
Cool. Can you all see my screen properly?
Yes, that looks good.
My slides?
Yep, perfect.
Amazing. All right. So thanks everyone for being here. So yeah, today in this seminar series, I will be talking about reinforcement learning for combinatorial optimization, in particular getting you through the foundation to this field to the current state-of-the-art method. So the overview of this presentation will be the following one. I will first get you through the context and motivation for all of this, particularly what is combinatorial optimization, why is this a challenge, and why can reinforcement learning be useful. Cool. Then I will get you guys through the evolution of reinforcement learning for combinatorial optimization over the years. In particular, what were the challenges with designing a neural network for this task? How was the training procedure designed? And what were the motivation to start using population-based approach and diversity rather than just like a single agent approaches. And finally, I will present you the current state of the art that we've been developing last year, which is called Compass. In particular, how is it solving the limitation of the previous approaches? How did we achieve to train like a continuous population of infinite agents? And obviously the result we got. So let's start directly with the context and motivation about combinatorial optimization. And first, the definition. So combinatorial optimization, which I will now refer to as CO, is about finding the optimal solution from a finite set of solutions. So optimal solution according to an objective that we will be trying to either maximize or minimize. And it's a finite set of solutions because usually the variables that we need to fix are discrete. And it's not because it's discrete that it's not big. Actually, the search space is usually enormous and is typically growing exponentially with the problem size. This type of problem, this family of problem, is extremely important because there are numerous use cases in the industry, which are usually crucial in terms of energy, time, and money savings. Which is why it's so interesting, so important for researchers and for companies to try to improve the way we solve them. All right, so now let me introduce you a bit better to the challenge of combinatorial optimization. So according to you, which of those two quantities is the largest? Is it the number of atoms in the observable universe, or is it the number of options to travel through 60 cities? It's actually the same. So in both cases, it's 10 to the power of 80, which is absolutely huge. And so how did I got those numbers? So for the number of atoms in the universe, got it from internet. And to compute the number of solutions to this problem, which is actually looks like a simple problem, but it's not at all. So let's say we fix the first city, which we can do because it's symmetric. Whatever the starting point, you can always obtain an optimal solution. Then you only have 59 remaining cities to visit. Once you've gone to this city, you've been to the city, there is only 58 remaining, etc., etc. So if you just multiply all those numbers, it gives you the 59 factorial, which is 10 to the power of 80. And keep in mind that TSP60 is actually quite a small instance for us researchers, and even more for the industry. In the papers, in the work we're doing, we never consider smaller solutions, smaller instances than TSP 100. And in this case, we are already reaching 10 to the power of 155. So yeah, two major issues. The first one that we've just illustrated is the very, very large search space growing exponentially. And the other one is that there is no direct gradient that is linking the solution created to the objective, because we are dealing with discrete variables. So now, can't we just solve this with like other mathematical tools, which would be like exact methods? For instance, a famous method to deal with a discrete variable is branch and bound. So you choose a first variable. I mean, you have like n variables that you can take. Try to take them, look at where you are, and kind of trying to prune the search space whenever you can. For instance, you find a first solution randomly, and then whenever you're trying to create a new one, you will stop looking at that path in the tree when you've got a partial toe length that is bigger than the solution you already have. So it is a simple way to prune your search space and continue like that until the budget is used. But this is way too simple. And overall, I'm not going to cite all the potential solutions to try to tackle those problems, but no known algorithm, no known exact algorithm can solve them optimally in polynomial time. So those problems are called NP-hard problems. And they would work fine for like TSP 20 or 30, but they would already struggle. I mean, they already struggle for more cities. Hence, the current best approach that is available in the industry is kind of a combination of heuristics and approximation algorithm and rules. So mix of rules, for instance, for TSP, you will never consider cities that are not in the nearest cities of your current location. So instead of considering always the 100 cities around you, you will only consider the 10 first cities. You can also use exact optimization locally. So you can try to solve exactly a subroute, and then use tricks like merging several subroutes to create an entire solution. Those approaches that we usually refer to heuristics, they can scale to large instances, typically more than 10,000 cities in the case of TSP. So they lose the proof of optimality, and they usually don't have performance guarantees, and they require years and years of development by experts. We can be talking about like 20 years of people that have PhDs, which is costly and takes a lot of time. And those are highly problem dependent. So even though you've had like brilliant people working during 30 years on a problem, there is a risk that all the rules they are going to come up with and all the tricks they are going to come up with, you won't be able to transfer them to the next problem. So the rules for TSP won't work for the rules for the job shop scheduling problem. Yeah, so that was the introduction to CO and the challenges of CO. Now a quick recall on reinforcement learning. I think you are all familiar with it, but just quickly. So it's a learning paradigm that uses the idea of trial and error, which is inspired by behavioral psychology. The objective is to learn a strategy called policy that is going to maximize the total collected reward in an environment. And an agent is typically going to explore different actions and adjust the way it chooses its actions based on the outcome it's had over the trials. The key component to use reinforcement is to express a problem with states, which correspond to the decision context one has when taking an action being the agent choice and the way the agent can interact with its environment. And this agent is going to collect a reward, which are the feedback it has to improve over time. And so, yeah, why is reinforcement promising for this class of problem? So as I mentioned, the current best way to solve those problems is to come up with a set of smart rules that are going to enable you to create an approximate solution to the problem. The thing is that you could encode those rules with a deep neural network that would take as input the problem at end, like the instance of the problem at end. And you could use reinforcement learning to update the weights of your neural network to create rules that are smart and that enable you to create approximate solutions that are very close to optimality. In that case, you would represent your problem with states that would be, sorry, in order to express this problem with reinforcement learning, you would introduce a state that would be a representation of your instance and of the current partial solution you're currently building. The action could be selecting the next node that you're going to visit, and the reward would be the quality of the final solution built. So this would be a way to build methods like solvers that would construct solutions. They also exist solvers that do improvements over existing solutions, but I won't mention them in this talk. And yeah, the overall objective would be like given a certain budget, so a number of attempts to build the best possible solution for the instance of the problem at hand. So here would be like the dreamed method, really our like targeted RL4CO method. In terms of performance, we obviously want to decrease the gap to optimality. So we want neural solvers that are going to produce the best possible solutions. We want a solver that is going to generalize, which means we'll be able to still maintain performance, even though the distribution of problem instances is different from the one it has seen at train time. We want a solver that is scalable, which means inference is fast and respect kind of decent hardware constraints, even when the size of the problem you're trying to solve is very large. And finally, and it's very important, we want a method that is versatile, which means one that the process we've been using to create our neural solver can be used whatever the problem we are trying to solve. I was telling you a few minutes ago that currently the heuristics used in the industry, they require years and years of domain expertise and like let's say expert time. We would like a method where the same algorithm can be used for different problems, for the TSP, for the GSSP, for the CVRP, whatever the problem. So even though you would have to use the process again to learn new weights of your neural network, new parameters, the process itself will be agnostic. It is very important for us and for the industry. So yeah, here are a bit like the kind of the overall challenges and also the objectives that kind of any researcher doing RL4CO would like to target. Now I'm going to get you through the evolution of this field over basically the past 8 years. A lot of things happened. And I will in particular get you through 4 milestone works that have been published in this field. The first one is pointer networks by Auriel Vignals from 2017. So here, quick disclaimer, there is still no reinforcement learning, but I think it's important to mention it because it was the architecture used was super important to kind of unlock good performance in this field. As a matter of fact, it's not obvious how to design architectures for solving those problems because you usually have like variable length in your input and output. So initial like classic MLPs are not very adapted for this. The thing is, this is kind of a similar setting as in natural language processing. So the field of RL4CO got inspiration from the field of NLP and from all the advances in NLP to design its architectures. In particular, so Vignals in 2017 introduced the pointer network to achieve this. So the idea in the pointer network is to use a RNN. So we are looking at the figure B here. To use a RNN, a recurrent neural network, to encode the nodes in a problem. So imagine here it's TSP with 4 cities. You're going to encode your problem and create like latent vectors, like embeddings of your cities. And then you're going to use attention mechanism to point towards the city you want to visit first. So once you're here, you're given a token that tells you that it's the beginning of the solution you want to build. And you're going to use attention to point your attention literally toward the city you want to visit. Then mask it, then point to the next city, mask it, etc., etc. And you use this mechanism to build a solution. So before I move to the next slide, just maybe some of you have recognized the name of the author. Vinyals is the co-lead of Google Gemini that was released 2 weeks ago. So a big name is in artificial intelligence. But yeah, this method was still using supervised learning, which means that when you want to train your model, you need to have access to perfectly solved problem instances, which is extremely costly. And what we want to do is outperform those methods that currently create the optimal solutions. So in a way, if we want to one day outperform them, it's important to use a learning paradigm that doesn't require those supervised instances, which is why reinforcement learning is such an important paradigm for CEO. So the next method that has been very important for this field is from the paper Attention, Learn to Solve Routing Problem. Here, again, inspired by the NLP community, very inspired by attention is all you need. So in this work, they use encoder-decoder architectures to solve those problems. So the encoder is a large transformer that is going to process the problem once. So for instance, if we still keep TSP as an example, TSP is described by the n cities, the coordinates of the n cities we would like to visit. And we will just give the coordinates of those cities as an input matrix. For instance, TSP 100 is going to be input of size 102 for the 2 coordinates. And this matrix is going to go through the transformer and create a big matrix of embeddings to kind of represent in a latent space each node we want to visit. And then we're going to use a smaller decoder, which is also based on the attention mechanism, to take the current context, so the states, the city you're currently at, and you're going to use this context to attend to the big matrix of embeddings. And this attention mechanism is going to output logits for each city, which correspond to the likelihood, like the likelihood of visiting each city, which in a sense represents the belief you have of visiting, like each actions to be the best action to take. And even though, so the encoding only has to be done once, and the decoding is done n times to choose the n consecutive cities. So in the case of TSP 100, it's done 99 times. And in order to optimize the parameters of those encoder-decoder architecture, we use the algorithm reinforce. I mean, they use the algorithm reinforce, which also being kind of an old algorithm in reinforcement learning, is still the common algorithm used even in 2024 to optimize those models. And I think recently there has been a paper or a tweet saying that reinforce is also very effective for LLMs. So it's interesting to see that these old algorithms are still, like in a sense, the best for some very important and recent applications. Then we move to POMO for policy optimization with multiple optima for reinforcement learning, which here doesn't update the architecture used. So the architecture is still the same, but it uses 2 tricks to improve the performance of the model through a better training. The first one is to use augmentation of the problem instances at train and test time. So it's more like a mathematical trick to use the symmetries that exist in the problem. And the other one is to try every possible first action in the problem. So for you that in TSP, there is also a symmetry in the first starting position you're using. every single starting point can lead you to the best possible solution. But the model is not is still sensitive to this first starting position. So the solution you're going to build through each starting position is potentially different. And so they use all the starting position to try to get the best one. What they also do is, thanks to all those solutions built with the starting position, they can algorithm. So in reinforce, you need the advantages of the action you're taking. In particular, when you're trying to learn, you're always comparing the value of the action you're currently taking to some kind of baseline, some kind of reference, because you want to know how good is this action compared to all the others. What is going to be my advantage of using this action compared to other actions. And actually, this trick of using all the starting position is helping you to build a better baseline in the reinforce updates. I think at this point, it's interesting, maybe if you guys have some questions, I can do a small break to answer maybe a first set of questions if relevant.
I think I'm good for the moment. Any questions from anybody else?
All good.
Amazing.
All clear. Thanks.
Cool. So until now, I've introduced you all to kind of let's say the state-of-the-art single agent solution in reinforcement for combinatorial optimization. But interestingly, the next paper is going to introduce a population to solve those problems. So this paper, winners Texito from Greenstein et al., which is actually our colleague at INSADIP, introduces POPI. So POPI, in POPI, the idea is to train a population of agents with diversity inside the population in order to increase the overall performance of the population. And the idea behind this is that those problems are so tough, so hard, they are NP hard. So you kind of have the intuition that it's almost impossible for any neural network, even with a huge capacity, to build an optimal solution on the first shot, to have enough capacity to understand the problem, the instances well enough to build an optimal solution. And the idea is kind of similar to divide to better conquer, is to have a population where each agent is going to specialize in a sub-distribution of instances. And through this specialization, this is going to create diversity, and this is going to build a kind of a team of experts where each expert is going to be the best on a sub-distribution. So when you're going to see a new problem instance, each expert is going to try to solve it. And obviously, there will be one very good at it. And you obviously expect this to implicate an increase of the performance you get on your problems. So this update the population, the objective that we are trying to optimize. And what's happening, let's say when you implement this concretely, is that instead of just rolling out one agent, collecting your transition and your action and rewards in the environment, and optimizing your agent to improve the expectancy of the rewards collected, you are going to roll out several agents, look at the performance they get when they are trying to solve the problem, and you will only train based on the one that got the best performance. So on the left, here is the kind of classic training paradigm. So as we mentioned earlier, there is an encoder. So this is like your problem instance that is encoded to create embeddings. And then there is a decoder that decodes n times to incrementally build the solution to the problem. Now in POPI, there is still an encoder that is going to create those embeddings based on the instance we're trying to solve. But then this matrix of embedding is going to be used by several decoders that are going to try to solve the problem. And in the end, we look at the reward obtained and we will train only this decoder if it has been the best. But when we are going to see like several problems, this problem is going to be the best maybe on the first problem, but it's going to be very bad on the next problem. But this decoder here is going to be the best on that new problem, etc., etc. And this enables to create naturally and without having to design diversity by ourselves, a natural diversity in the population that is going to help creating a performing population. So in a way, all the agents are going to specialize on subdistribution. So even though they are expected to perform worst alone on the global distribution, as a team, they should perform much better. And they do perform much better. And there is also interesting tricks here, like no need to train the population from scratch. So interestingly, this work, Poppy, is reusing the exact parameters from POMO. So when the POMO code was released and the weights of the neural network were released, Poppy just reused those weights to initialize its population of agents. So it's an interesting way to reuse previous computation.
Sorry, can I just ask a question here just for clarification? So you have a particular problem instance. You encode that, and then you've got a number of different agents, each of which attempts to solve the problem by essentially giving a route, if you're looking at the traveler and salesman problem. So each one gives you some route, and there's some reward in essence for each of them corresponding to the path length or whatever. When you say then that you only train that agent that has the highest reward, what do you mean training in that sense? In that it's now come up with a solution? Are you then using an RL algorithm on top of that to train that single agent to improve on its original solution?
Yeah, exactly. So just as if it was like a single agent problem, we would only so for this particular problem, like instance, the data would be used to train that agent. So in practice, it's more the other way around. It's like we've got a big batch of problems. So we expect like every agent is the best for on at least one problem. And then we at the same time estimate the gradient for all the agents and for the encoder.
So in a sense here, although there are multiple agents, they're not interacting in any way?
No, yeah, they are not.
Okay, yeah, thanks.
Exactly. Yeah, that's a very indeed important point. This is not a multi-agent reinforcement learning. It's really like population-based reinforcement learning. And there are indirect interaction in the sense that agent 2 is not trained because agent 1 is trained, but there is no direct collaboration or interaction.
Can I just quickly ask, if they're all initialized to the same parameters, how do they differentiate?
It's also a very good question. The answer is thanks to stochasticity in the rollouts. So just as a usual reinforcement training, a noise is used when we roll out the agent in order to ensure exploration. And in our case, this noise is also useful because at the initial step, indeed, all the policies are the same. So the only way to make them slightly different is the noise used during the rollout. And if ever they happen to be having the same performance, initially the Poppy was just training arbitrarily the first one. Literally they are ordered, they have indices 1 to whatever. Was just training the best one, the first one, sorry. But actually in the follow-up work, they decided to not train the agent when there is a tie. So if ever with stochasticity, you're still having the two agents have the same performance, then no one is trained. And this kind of further improve the specialization of the agents. All right, so I just got you guys through those 4 kind of building blocks for this field. So with kind of the architecture used to solve those problems, the reinforcement algorithm used to solve those problems, and how having a population rather than a single agent can help get even better performance. Now, there are still drawbacks of this method, POPI. In particular, 3 drawbacks. The first one is the limited scalability of the method. So if you want to have more specialization, you want to train more agents, which means it requires to train even more parameters and even more gradient updates. And you also need more like bytes to store in your RAM. So this is definitely a limitation of this method. Also, you have like very limited adaptation under a given budget. So usually you train your agents. So this is training time, and then you've got inference time. At inference time, you're given a budget to create the best possible solution. So you don't roll out your agent only once to create a solution, but you're allowed to roll it out like several times. The thing is, with POPI, you just take your population and you roll it out on the problem. If you only have like a small budget, you do it greedily. If you got a big budget, you do it like stochastically in order to still explore. But like this is like very limited. If you're given an even bigger budget, you're just going to continue rolling out stochastically, and you're gonna have like a very limited or like inexistent improvement over time. And consequently, there is also like limited generalization capacity because as you're having like a discrete and small population size, if you're evaluated on a distribution that you know because you've seen it at training time, you are likely to be good on it. But now if you're evaluated on a new distribution, like instances from distribution you have never seen, it's kind of unlikely that one of your like agents is going to be good on it. So you can see that even though it's I think it's a very good method, there are still like a few drawbacks that we think we can definitely alleviate. And that's where Compass arrives with this idea of introducing not an explicit and discrete population, but an implicit population that can be armed with a latent space search. So let me just quickly give credit to all the team. So the paper is called Combinatorial Optimization with Policy Adaptation using Latent Space Search, which creates the acronym Compass. And it was done last year with this team. So myself, Shika, Clément, Nathan, Arnaud, Alexandre, and Thomas. And we have been able to present our work at NeurIPS in December last year. So here the idea, as I quickly mentioned, is to learn a space of diverse policy. So instead of having a discrete number of agents, it's going to be a potentially infinite number of agents encoded in that space. And we want to make sure that that space can be explored at inference time, so that we can use our budget to explore the space in order to find the most performant policy in that space for a given problem instance. So what about the 3 drawbacks I just mentioned before? Concerning the limited scalability, we are conditioning the policy with a latent vector. So even instead of having like several neural networks, we're going to have only one neural network that will be conditioned with a latent vector. Hence, each value for this vector is going to impact the output and create a new agent, a new policy. And given that we are sampling the latent vector from a continuous distribution, this means we can potentially have like an infinite population. Now I was mentioning also the limited adaptation under a given budget. If our space is well-defined enough, it should be able to be explored while the budget is consumed. Hence, by like kind of updating the distribution, we are sampling the latent vector from. And yeah, I was also mentioning the limited generalization capacity. We can't, obviously, we can't ensure generalization on an unseen distribution, but given that the population is potentially infinite, the likelihood of finding a good policy for a new problem much higher than before. All right, so let's now dive a bit like in depth into this method and how Compass works. So we are still under those two phases. So the training phase, the one that can take weeks if we want, in which we are going to train we want to train this continuous space, this implicit population of diverse and specialized policies. And then we'll talk about the inference, where we want to very efficiently search the space to find the most performing solution with a limited budget. So first, the training phase. So what we do is that we first define a latent space. This is a prior. So we typically take a uniform distribution from a 16-dimension space, like uniform distribution between -1 and 1 with 16 values. So very simple, and it's fixed. So at each step, we sample a few values from this space. For instance, let's say 16 values or 100 values. Sorry. We will then use those values to condition our neural network. So each values after the other, we're going to condition the neural network. So hence creating a new policy. We're going to use it to roll out our policy on the given instance and to take the solution. We do this for all the latent vectors. So we collect those n solutions. So let's say 16 latent vectors, 16 solutions. And just like Poppy was doing, we are going to train only the latent vector that got the best performance, because we want to keep the specialization objective, which is what we do. So yeah.
Sorry, can I ask this? So you say you're training the latent vector. So by that, you mean you keep the weights of the network fixed, but you're just updating the latent vector?
Thanks for the question. Yeah, I was actually doing a kind of a simplification. So as I said, the latent vector, the latent space is fixed. So it's not the latent vector, the latent space that is updated, but it is those are the weights of the neural network. So yeah, thanks really thanks for asking this question. So I'm like everything is going to be. So yeah, latent space completely fixed. The weights of the neural network need to adapt, need to change in order to create the specialization in that space. So yeah, once the latent vectors have been sampled, the corresponding policies have been evaluated and ranked. We only train the policy, so the neural network, based on the data that correspond to the best solution and best latent vector. And we continue to do so until we've converged. Interestingly, this method is quite stable. Like we never had any stability issue by doing so. So most of our efforts were more like how to create the biggest possible gap, the best possible specialization, and how like making sure that our space would be kind of regular enough to be explored. But the process in itself was kind of stable, which was pretty convenient. All right, so now that we are given a neural network that has been able to create this specialization in this fixed latent space, let's see how we can efficiently explore this space to find the best possible solution for a new instance at end. So we delve into the inference part. So initially, we sample latent vectors in our given space. And same, we condition our policy, like our network, based on those latent vectors. We collect solutions that we can also rank. And based on the rank of the solution, we can actually update our belief on which part of the latent vector is enabling to get the best possible performance on this new instance. So, for instance, here for our given problem instance, let's say this area here in red would be the best possible latent vector. to solve the problem. So at first, we're going to sample in random areas, which are not necessarily the best one. But little by little, we can update the distribution to get closer and closer to those area of high performance, which is what we do until the budget is used. So now let's look at the result we can obtain with this idea. So we've been looking at 3 types of problems that are very popular in this community. So the traveling salesman problem, the one I've been using for all my explanation, but also the capacitated vehicle routing problem, the job shop scheduling problem as well. Well, I won't dive into the detail of those problems because we already have been using like almost 40 minutes of our time today, but you can always look at the paper if you want more details. And then the baseline we compare to are POMO, POPI, and also EAS, which is a method that is also used to adapt given a budget. And those are basically the 3 best performing solution methods for like a neural solver that want to construct solutions. And here on the spider plot, we represent kind of the performance of all those methods for different tasks. So those aggregates the 3 problem, the 3 CO problems mentioned, TSP, CVRP, and GSSP, on different tasks. So the one is the performance in distribution, the other being like all the other being out of distribution, but out of distribution because the instances are larger than the ones seen at training time, or they have been transformed with like a shift, like mutations. And also there is the few shot task. So basically all those are like a large budget, and few shot means a very small budget. And interestingly, we can see that Compass is able to outperform all the other methods on all those tasks. And in particular, the important task of generalization. And if we dive a bit more into the generation abilities of this method, so what we did is that so those methods are usually trained with a random uniform distribution. And what we did is that we mutated the instances in order for them not to be uniform at all. So we used explosion, implosion, but also 9 others way to mutate those instances. The good thing, like the interesting thing with the mutation is that you can control the power of this mutation. And when you increase the power of the mutation, you also increase the divergence between the 2 distributions. And we've been doing this to see if when you increase the mutation power and hence the out of distribution S, is Compass outperforming even more the other methods. And interestingly, it is the case. So if we look at this plot here, on the y-axis, we've got the performance ratio between each method, like compared to Compass. And on the x-axis is the mutation power. So how out of distribution are you on this case? And we can see that the performance gap, like the performance ratio, is increasing compared to Compass when the mutation power increases. And this is the case for TSP and CVRP, which kind of prove that Compass is more robust to out of distribution and does indeed generalize better than the other baselines.
Does sorry, Felix, to interrupt us on the slide. Does Compass's performance also decrease as you increase the mutation power? Just because this, obviously, from this graph, it won't show that.
Yes. So compared to an initial solver, compared to optimality, when you say
yeah, that's what I mean. Like the gap to optimality.
Okay, gap to optimality. Yes, it does. It does increase. So it means that there is still room for improvement. So then let's have a quick analysis on the search process, because remember, one of the desiderata we had for this method was to create a latent space that would be diverse and specialized. but that would also be that we could explore at inference time. So here what we do is we basically solve a set of instances, and we look at the performance obtained over time. And I think I will just suggest that we just look at this plot on the right, which is the performance of the last solutions that you've been generating. If you look at Pomo and Poppy, the performance is always the same over time. So if you are at the beginning of your budget or at the end, your performance is the same because you have no adaptation mechanism. You just sample stochastically. So yes, your aggregated performance is increasing because with luck, you're going to find better and better solution. But the quality of the latest batch you're producing is always the same, no adaptation. EAS is a method that is doing fine-tuning. So it's basically doing reinforcement learning again at inference. So it's very costly, very, very costly. It changes the weight of the neural network for each single problem instance. So it's costly in terms of time and also in terms of memory. So yes, it adapts, but not that well. And it's also very costly. And Compass here in red, which is, by the way, like 4 times faster than EAS. You can see that it's able to adapt little by little and reach a very good like quality of the solution produced. And let's look at this, let's say, fancy plot, which is here to represent the quality, like it's kind of a heat map of the latent space that shows which areas of your latent space are high performance for the problem you're trying to solve. So it's a bit the equivalent of you know, here what I was showing you here. So indeed, there exists specialization. You can see in blue here that if you sample the latent vector from this blue area, you're going to have bad performance, whereas here in red, you're going to have a much higher performance. And there is, so here with those blue, with this white path, I'm representing the evolution of the distribution we've been using to sample those latent vectors. So this distribution is a multivariate normal distribution here in a 2D space. And the cross represents the mean of this distribution, and the thickness of the path represents the covariance matrix. And you can see that at first, we had a big desire to explore the space. So we're sampling from a very broad distribution. And little by little, the mean got closer and closer to the optimal area. And also, the covariance used to sample the latent vectors got smaller and smaller. We are really focusing our sampling in this area of high performance. All right, so now what are the next steps, which are kind of related to potential weaknesses or unexplored capacity of Compass? So overall, the goal of this field would be to solve like very big instances. I was mentioning during the introduction that industrial solvers are able to solve like to reach very good performance for problems that have like 10,000 cities for the TSP. Here in our paper, we focus on instances that have in between 100 and 200 cities. So we are still kind of far away from this. And if our RL solvers want to achieve this, they also need to be trained on larger instances. So this is still like something that this field need to achieve. And another thing that is very kind of Compass specific is that the degree of specialization we are going to achieve during training is going to be very linked to the data we are using during training. And if this data become diverse, we believe that Compass should be able to create a latent space that is going to be even more specialized. So Compass performance is linked to its specialization, which is itself linked to the data seen at training time. For those two reasons, there seems to be promising things to achieve by working on the distribution of instances that is used to train Compass. And yeah, that was maybe some of you got it, kind of a teaser for a project that is about to be hosted by the Shocklab. So yeah, let's just finish with a few take-home messages, 3 simple messages. First, a very general one, which is that CO, so combinatorial optimization problems, correspond to a very challenging class of problems. Challenging, but with many very important applications in the industry. So it's super important to really put some effort to improve the tools we have, to improve the way we solve those problems. The other second important message is that reinforcement learning, this learning paradigm that we all really are all very interested in, is a very good candidate paradigm to crack those CO problems. And finally, this method Compass that we've been working on for the past year is the current state-of-the-art method for those problems. The idea is to train and explore a latent space of specialized and diverse policies, and we've been able to prove that it reached like overall state-of-the-art on 29 tasks, including important generalization tasks. So yeah, thank you very much for your time and for your attention. And if you have any question about this talk, don't hesitate to ask them now or just to reach me offline whenever.
Wonderful. Thank you very, very much. That was fantastic. I have a quick question which I'd actually put in the chat, but it's actually more general than what I wrote in the chat. So let's say you're in your latent space and you pick a particular point in your latent space that essentially corresponds to some algorithm. You can think of it as sort of that corresponds to an algorithm. Is there any way to think about interpretability? So one problem instance will be best solved by a particular point in that latent space. Is there any way to interpret the latent space? So, points over here correspond to certain types of problems and other points over here correspond to different sort of problems. Is there any way that you can map out in the latent space and therefore use that knowledge given a new problem instance to pick starting points in the latent space that are going to be most likely to solve that type of problem?
Yeah, so it's something we haven't done, but that would be super interesting to look at.
Mm-hmm.
So we haven't done the analysis. We've tried very quickly, but at the beginning of the project, to kind of link the latent space with the type of the kind of the shape of the problem we are solving. But we didn't try again at the end of the project. It might be kind of tricky because it's potentially very hard. Like one of the ideas behind this population and creating this diversity is also to say we're not really sure how to perfectly solve this problem. So let's create some specialization, like a priori, as a prior thing, that like a prior tool we have. And then when we see the problem, we can try to use those different specialized policy to solve it better. So I fear it's actually too tough to create a model that has enough capacity to find directly the part of the latent space that is the adapted one. I fear we might just bump into a capacity wall.
Interesting. Sure. Thank you. I think Tim had a question there.
Yeah, sorry, I was just going to ask, when you're in evaluation, you talk about you're sampling points in the latent space, and then you're able to kind of move around the latent space. Are you doing some kind of gradient descent on the latent space, or how are you picking the direction to move in the latent space?
Yeah, good question as well. So we are using an evolution strategy. It's called CMIS. So we are using, it's called covariance matrix adaptation. So yeah, that's kind of what I explained with only a broad word without using the precise terms. But yeah, you've got a distribution defined by your mean and your covariance matrix. And so you sample from this, collect your points, you rank them, and then you use this ranking and some associated weights to update the mean and to update the covariance matrix. So the rules are basically when you've got all your the latent vectors with the rank, you're going to update the mean to be closer to the latent vectors that gave the best solutions. And based on the spread of the latent vectors that had good performance, you're gonna know if you're in like close to an optimal or not. So if it's kind of spread around, you're gonna increase your confidence matrix to continue exploring. But if you see that the distance is kind of trying to shrink, then you're gonna also shrink your confidence matrix to start exploiting. So that's why at first we would see that the optimization path was really getting thicker and thicker. And at the end, you could see that it was getting smaller and smaller. So yeah, we are using a CMDS.
That makes a lot of sense. Thanks.
Noah.
Yeah. So I guess my question kind of follows on from these two quite nicely. So obviously the CMS, the algorithm, the search algorithm there is completely abstracted to the model. It has no idea that the search algorithm is going on. Would there be a way to incorporate that in training? Because also my first question was also, well, what I was also going to ask is are the latent vectors during training always randomly sampled? Because if you were to allow a search algorithm during training, would that not make the latent space more well-defined? And kind of answering the question, because it maybe at the end of training, you train the best latent space, the best latent vector that was found for a given budget. I guess that's more of a statement and less of a question.
No, it's fully true. It's a very good point that I can elaborate a bit on if you want. So indeed,
sorry, just quickly, folks, I'm afraid I have to run. I've got another meeting starting in 2 minutes, but I can leave this running. Felix, I would love to talk about this more. I guess you and myself and Noah will talk soon. But from me, thank you so much again for a really good talk. I'm going to leave, but I'll let others continue. Thank you so much. Bye for now.
Thank you so much. Have a nice day.
Bye. You too.
So yeah, Noah, very good point. Indeed, there is like no awareness